Hello students, welcome to the session, welcome to Gradeup. Sorry, it got delayed 5 minutes due to the technical issues. I hope you're waiting. So, hi Raghunath, hi Vivek, hi Supriya. Yes, so we came back again. So, in today's session, we are going to see the working principle of gas power plant and the Brayton cycle. Hi all, I think for the newcomers or for new students, just a small introduction on me. Myself Damodar Rao, I did my MTech from IIT Guwahati. I have been teaching and mentoring GATE aspirants for 10 years. So we have been conducting the YouTube live sessions for GATE 2020 aspirants. So just for revision and to improve their score. Yeah, hi all, good evening. So today we are going to discuss about gas power plant and Brayton cycle. So let's start with the session. So we'll discuss about the things later because it's already delayed. So we are left with 114 days. I hope your preparation is on full swing. So I will start with here gas power plant. So simply a plant produces power by using gas as the working fluid. A simple definition. A plant produces power by using gas as the working fluid. We know that, right? We need a medium in order to have energy transfers. So here in gas power plant, we use gas as the medium. That gas is known as working fluid. In case of steam power plants, we use steam as working fluid. In case of gas power plant, we use gas as working fluid. In case of IC engines, we assume that air as the working fluid, right? So let us see what is gas power plant and how it works, and then we'll see how to deal with and how to analyze the Brayton cycle. So this is a simple construction of Brayton cycle. Here I have shown the 4 essential components which are required for running a gas power plant: cooler, compressor, combustion chamber and turbine. So which are 4 essential components which are required for running a gas power plant. First let us see how it works, and then we will see how to draw the Brayton cycle and how to deal and how to analyze the Brayton cycle. So initially what we do is, here we supply some work to the compressor, that is WC, so that the compressor starts running and compressor starts taking gas from the cooler. So the cooler, at the exit of the cooler, the gas will be at the minimum temperature. It will be at the minimum temperature, the lowest temperature possible in the cycle, so that it is a cool air or cool gas, and it is taken by the compressor. Now the compressor increases the pressure of this gas from cooler pressure to combustion chamber pressure. The compressor increases the pressure of the gas from the cooler pressure to combustion chamber pressure. Let us say that the gas leaves with the state 2. Let us say that the gas leaves with the state 2. In the combustion chamber, we supply some heat to the system. We supply some heat to the combustion chamber. This heat is absorbed by this gas. On absorbing this gas, the temperature of the gas starts rising. On absorbing the gas, the temperature of the gas starts rising, and it reaches to the maximum temperature in the cycle at the exit of the combustion chamber, and it leaves with the maximum temperature. And of course, while absorbing the heat, we maintain the constant pressure, because the combustion chamber is a heat exchanger. In heat exchangers, we maintain the constant pressure. So while absorbing the heat, we maintain the constant pressure. At the constant pressure, it absorbs heat in order to reach the maximum temperature of the cycle. Okay. So at the point 3, we see that high temperature gas. we see that high temperature of the gas, high pressure, high specific volume. We see that high temperature, high pressure, high specific volume gas. Now this high temperature, high pressure, high specific volume gas enters the turbine and it expands isoentropically in the turbine. While expanding, it does some work in the turbine. That is work done by the turbine WT, and it expands isoentropically until the pressure drops down to cooler pressure. So let us say that at the exit of the turbine, we have the state 4. We have the state 4. Now with this state 4, it enters the cooler. In cooler, we use some cooling system. To that cooling system, gas rejects heat. To that cooling system, gas rejects heat in order to reach the minimum temperature of the cycle. The gas rejects heat in order to reach the minimum temperature of the cycle. While rejecting the heat, again, the pressure is maintained as constant in cooler. Right? So, by now it completes one cycle. It started with 1 and it ended with 1. By now it completes one cycle, and during this cycle you can see here, so there are 4 processes in 4 components. You can see in the compression we see isentropic compression, combustion chamber constant pressure heat addition, in the turbine isentropic expansion, in the cooler constant pressure heat rejection. So we see that 4 components, 4 energy transfers and 4 processes. Now let us draw all these 4 processes on TS coordinates or pressure volume coordinates in order to analyze the cycle. Right? So again I am repeating here. We have 4 components and 4 processes. So we can see there are 2 work transfers and there are 2 heat transfers. 1 heat supplied to the system, 1 heat rejected by the system, 1 work supplied to the compressor, and 1 work done by the turbine. Right? So 2 work transfers and 2 heat transfers. 2 heat transfers happen at constant pressure. 2 work transfers happen at isentropic. One is isentropic compression and another one is isentropic expansion. Right? Now let us draw all these processes on the TS coordinates in order to analyze the cycle. So let me draw here. Take the TS coordinates to draw all the processes of this gas power plant, either in gas power plant or in steam power plant. So first we need to draw 2 constant pressure lines, because either steam power plant or gas power plant, they always operate between 2 constant pressure limits. So in case of steam power plants, we see that the power plant is operating between the boiler pressure and condenser pressure, and in the gas power plant we see that it is operating between combustion chamber pressure and cooler pressure. Okay. Now let us draw 2 constant pressure lines here. Draw 2 constant pressure lines. One is the combustion chamber pressure and another one is cooler pressure. We know that the constant pressure lines on the TS coordinates are like this. Okay, with the positive slope. So let us say that, one second. Okay, let us say that this is the minimum temperature of the cycle and this is the maximum temperature of the cycle. Okay, so now the process starts from the cooler pressure and minimum temperature. This is the state 1. Where do you have the state 1? The cooler pressure and minimum temperature. So this is the state 1. From this state 1, here the compressor takes the gas at the state 1 and the compressor increases the pressure of the gas from the cooler pressure to combustion chamber pressure. Compressor takes the gas from the cooler pressure to combustion chamber pressure and it increases the pressure isentropically to combustion chamber pressure. As we have entropy on x-axis, isentropic is nothing but constant entropy process. So for constant entropy process, we see that a vertical line on TS coordinates. On TS coordinates, we see a vertical line for isentropic compression and it leaves at the combustion chamber pressure. Now with the state 2, it enters the combustion chamber. In the combustion chamber we supply heat. This heat will be absorbed by the gas, and on absorbing the gas, the temperature of the gas starts rising and it reaches to the maximum temperature of the cycle. Right? So it starts here. We start supplying heat from the state 2 at constant pressure. So along the constant pressure, it reaches to maximum temperature. Let's say that is the state 3. With the state 3, it enters the turbine and it expands isentropically to cooler pressure. It stays state 3 it enters the turbine and it expands isentropically to cooler pressure. Let's say that is the state 4. So it expands isentropically. Again, we have entropy on x-axis. Therefore, entropy isentropy process takes a vertical line. Now let us say that this is the state 4. Now with this state 4, it enters the cooler. In the cooler, we use cooling system. To that cooling system, the gas rejects heat. On rejecting the heat, it reaches to the minimum temperature along the constant pressure again. Along the constant pressure line, it reaches to the minimum temperature of the cycle. Right? By now it completes one cycle. Right? In this cycle, what happens? So total 4 energy transfers. 4 energy transfers. Here 1 to 2 work supplied to the compressor. 2 to 3 heat supplied to the cycle. 3 to 4 work done by the turbine. And 4 to 1 heat rejected by the cycle. So 4 energy transfers and 4 components and 4 processes. This is TS diagram for a simple gas power plant. When you use all these conditions and when you draw a cycle, this cycle is known as Brayton cycle. What do you call? This cycle is known as Brayton cycle. There was a scientist called Brayton. He developed this cycle, so on his name we call it as Brayton cycle. Alright? So now let us see what are the energy transfers across all these components. What is the work transfer to the compressor, work transfer across the combustion chamber, what is the work transfer across the turbine, heat transfer across the combustion chamber, heat transfer across the cooler. Right? So now let us see. Maybe let me rub it off. So you can post your doubts while I was explaining, so that I'll see and I'll solve your doubts. So you can post your doubts in chat box. Sir, is it necessary to take the compressor work as it run by the turbine and as compressor work is small? Hi Chandan Sharma. You're right that so a partial work from the turbine is used to run the compressor, but at the same time compressor work is not small. So it takes significant work. Okay, if it is a pump, in case of the pump requires generally less work compared to the compressor, so we can neglect the pump work. But in case of compressor, we cannot neglect the compressor work because the compressor requires a significant work. Right? Now let us see the energy transfers. So why 3 is the high pressure point, Sharmila? So 2 to 3 is a constant pressure line and the combustion chamber operates on the high pressure side. So from 2 to 3 it's the high pressure only. Just not only just 3 is the high pressure point, but 3 is the point where we see all properties are high. High pressure, high temperature, high specific volume. Okay? Now, let's see the energy transfers across the components. Okay, so starting with process 1 to 2, let us take the process 1 to 2. What is the process 1 to 2? Isoentropy compression. Process 1 to 2 is isoentropy compression. Ishak, I will explain the PV diagram also. Okay, just first let us write all the energy transfers and then we can write PV I can explain PV diagram also. The efficiency of the Brayton cycle will be derived. Aravind, just wait. Yes, Arvind, will derive the efficiency. Yeah, right? So now 1 to 2 is isoentropy compression. So that 1 to 2 we see that isoentropic work. So 1 to 2, what is the isoentropic work? WC, that is work supplied to the compressor, is mCp into T2 minus T1, either in kilojoule per second or joule per second, depends on the units you have substituted. You'll get either kilojoule per second or joules per second if you have made the mass flow rate. Okay. Now process 2 to 3. What is 2 to 3? That is constant pressure heat addition. Constant pressure heat addition. So that here we have to write here heat supplied to the cycle. Just not that heat supplied to the combustion chamber. You always practice that heat supplied to the cycle. Okay, that is heat supplied to the cycle in a constant pressure process is m into Cp into T3 minus T2, either in kilojoule per second or joule per second. This is the heat supplied to the cycle during a cycle. Right? Now take the process 3 to 4. What is 3 to 4? Isentropic expansion. So during the isentropic expansion, it does some work in the turbine. Therefore, work done by the turbine, Wt is equal to m dot into Cp into T3 minus T4. That is in kilojoule per second. Okay, this is the work done by the turbine during an isentropic process. What is the difference between Carnot, Rankine and Brayton cycle? Raja, Imba Raja. Okay. So the Rankine cycle is a working cycle for steam power plant, and the Brayton cycle is the approximation cycle for gas power plant, and Carnot cycle is an ideal cycle for all the cycles, all the heat engines. Okay. So these three are three different things. Brayton cycle is the approximated cycle for gas power plant. Rankine cycle is the approximate cycle for steam power plant, and Carnot cycle is an ideal cycle for all the heat engines. I hope you got it. Right? Now let's take the next one. That is heat rejected by the cycle. If something you are missing, or if something is not, if you miss anything, whoever joined lately, so it will be recorded and it will be available in the YouTube also. So after the class, you can have a revision. Okay. Now take the 4 to 1. What is the process 4 to 1? Heat rejected by the cycle. Okay, it is a constant pressure heat rejection, and heat rejected by the cycle, Q rejection is equal to NCP into T4 minus T1 in kilojoule per second. This is heat rejected by the cycle. That's it. We have 4 components, 4 processes, 4 energy transfer, nothing else. What do you see? There are 4 energy transfers, 4 processes: isentropic compression, constant pressure heat addition, isentropic expansion, constant pressure heat rejection. So for 4 processes, 4 energy transfers. That's it. The problem is over. Satyendra, isentropic during the isentropic process, what is the equation? Okay, Satyendra, tell me, what is the isentropic process for? So isentropic work, generally write it as P1 V1 minus P2 V2 by, so gamma into P1 V1 minus P2 V2 by gamma minus 1. So I can write it as gamma into MR T1 minus MR T2 by gamma minus 1. So let's take MR common here. M into gamma R by gamma minus 1 into T1 minus T2. So what is gamma R by gamma minus 1? Cp. So that it is equal to MCP into T1 minus T2. Right? So that is how it has come. Now, what else you want from the power plant? What we look for power plant? We look for net work output of the cycle. What we look for? We look for net work output of the cycle. Now let us write the equation for net work output cycle. Net work output cycle is, what is net work output cycle? Net work output of the cycle is equal to sum of all work transfers or sum of all the heat transfers. From the first law of thermodynamics, sum of all the heat transfers is always equal to sum of all the work transfers in a cycle. So that net work output is always equal to either sum of all the work transfers. What is the sum of all the work transfers? Wt minus Wc, or you may write it as sum of all the heat transfers, Qs minus Q rejection. Very simple. Either sum of all the work transfers or sum of all the heat transfers. Wt minus Wc or Qs minus Q rejection. What is Qs minus Q rejection represents here? We know that heat transfer during a process is nothing but area under this curve on Ts coordinates. So area under this curve is the Qs, area under this curve is the Q rejection. When you subtract this area from this area, we will remaining with this area. So that this area of the cycle on Ts coordinates gives you net work output of the cycle. Right? So net work output, let me write in terms of temperatures, MCP into T3 minus T4 minus T2 minus T1. Either you can write in terms of heats, in terms of works. This is the net work output of the cycle. Now let's go to the thermal efficiency of the cycle. Yeah. Yes, Hanuman, heat rejection is always negative. Okay? But here we are already writing heat rejected by the cycle. So you don't need to use again a negative sign here. When you are using a negative statement, again you don't need to say that, you don't need to write in the equation with negative sign. Okay? Yes, I am going to cover Rankine cycle also, because we have planned more and more YouTube live sessions. So in those sessions we will see remaining topics also. Now let's take thermal efficiency of the cycle. Okay, thermal efficiency of the cycle. What is thermal efficiency cycle? Can anyone tell me? Thermal efficiency cycle is nothing but net work output by heat supplied. So we are calculating thermal efficiency for Brayton cycle. Let us take eta B, which is equal to net work output by heat supplied. Thermal efficiency in any cycle is always the same equation. It is always the net work output by heat supplied. Or what is the net work output? Heat supplied minus heat rejection by heat supplied. Or I can write it as 1 minus heat rejection by heat supplied. Right? We can write it as 1 minus heat rejection by heat supplied. So what is the heat rejection? So I can write here MCP T4 minus T1 by T3 minus T2. That is nothing but T4 minus T1 by T3 minus T2. Hi Munai, this class going will continue up to 6 o'clock. Okay, half an hour more. So now let's try to find out the thermal efficiency of cycle. Thermal efficiency cycle we can write it as, let me take here T1 common from the numerator, T3 common from the denominator, so that I can write here T4 by T1 minus 1 by T3 by T2 minus 1. Okay, so we can write, just take the T1 common from the numerator, T2 from the denominator. So T2 from the denominator, so that it will be T3 by T2 minus 1, and here T4 by T1 minus 1, right? So in order to find out thermal efficiency cycle, we need to have these ratios, T1 by T2, T4 by T1, T3 by T2. If you have these ratios, you can find out thermal efficiency of cycle, right? So let us see what are those ratios. For that, let us take the process 1 to 2 again. Let's come back. What is process 1 to 2? Isoentropy compression. Isoentropy compression is nothing but P power of gamma is equal to constant, right? So in an isoentropy compression, can I write T2 by T1 is equal to P2 by P1 whole power of gamma minus 1 by gamma? The relation between the pressure and temperature, T2 by T1 is equal to P2 by P1 whole power of gamma minus 1 by gamma, right? So here the ratio P2 by P1 is known as, what do you call? Is known as pressure ratio of the cycle. It is known as pressure ratio of the cycle, and it is denoted by Rp. This pressure ratio of the cycle, and it is denoted by Rp, so that I can write T2 by T1 is equal to Rp power of gamma minus 1 by gamma, right? Now let us take the process 3 to 4. What is process 3 to 4? Again isentropic process. It is an isentropic expansion. So in an isentropic expansion, I can write T3 by T4 is equal to P3 by P4 whole power of gamma minus 1 by gamma. Again, from the isentropic relation between the pressure and temperature, T3 by T4 is equal to P3 by P4 whole power of gamma minus 1 by gamma. Rahul, the difference between the perfect gas and ideal gas. So both are same. The gas which obeys the perfect gas law or ideal gas law is known as perfect gas or ideal gas. They are the synonyms. Sir, is it possible to get the GATE syllabus in time? Yes, here we are going to cover, or we are going to make you practicing more and more problems, which magnifies your score. So that is what we are trying. Right? So coming to this here, the T3 by T4 I can write P3 by P4 whole power gamma minus 1 by gamma. But what is P3 by P4 here? P3 by P4 is nothing but, you can see what is P3. P3 is nothing but P2, because we have a constant pressure process here. P2 is equal to P3, P1 is equal to P4, right? So that P3 is equal to P2, P1 is equal to P4. Therefore, I can write P2 by P1 whole power of gamma minus 1 by gamma, which is equal to Rp power of gamma minus 1 by gamma only. Right? That's it. What do you see here? Here T2 by T1 is equal to Rp power of gamma minus 1 by gamma. T3 by T4 is equal to Rp power of gamma minus 1 by gamma. What does it mean? It means that T2 by T1 is equal to T3 by T4. So from this I can write T4 by T1 is equal to T3 by T2. Right? So we came to know that T4 by T1 is equal to T3 by T2. So when you see the efficiency equation, when T4 by T1 equal to T3 by T2, this will get cancelled, and our efficiency will become 1 minus T1 by T2, or what is T2 by T1? Rp power of gamma minus 1 by gamma. This is the thermal efficiency of the Brayton cycle. Got it? This is the thermal efficiency of the Brayton cycle. Yes, Shivareddy, we are going to provide all thermodynamic classes, so stay connected with Gradeup. Right? So this is the thermal efficiency of the Brayton cycle. Now when you see that this thermal efficiency of Brayton cycle is a function of pressure ratio and function of gamma, right? So now I can write here thermal efficiency is a function of pressure ratio and gamma. Okay, so I can write here thermal efficiency cycle is the function of pressure ratio and gamma. But for a given working fluid, if the working fluid is fixed, then gamma is fixed. If the working fluid is fixed, so gamma depends on working fluid only. So for a given working fluid, this Brayton cycle is always function of pressure ratio. It's just a function of pressure ratio only. So what you see here, when the Brayton cycle is a function of pressure ratio, so how it relates? When the pressure ratio increases, what about the efficiency? When the pressure ratio increases, the Brayton cycle efficiency also increases. We see that the efficiency is directly proportional to the pressure ratio of the Brayton cycle. If the pressure ratio increases, the efficiency also increases. That means if you maintain more pressure ratio, we can see the more efficiency, right? That means we can play with here pressure ratio. So by increasing the pressure ratio, let us see how much efficiency we can increase. It is downloadable after the live class. Yes, it is available. Yes, you can practice by taking any material which is available, Rashekar, which is available in the market. You take any material. So the gate materials which are available, you can practice there. Okay. So now let us see. Let us play with the pressure ratio of the cycle. So for that, let me draw another Brayton cycle. So by taking the TS coordinates, so what you see here is the maximum temperature is fixed and the minimum temperature is fixed. Let's say this is the minimum temperature and this is the maximum temperature of the cycle. So here let's draw a constant pressure heat addition, isentropic expansion, and constant pressure heat rejection. 1, 2, 3, 4. This is a simple Brayton cycle. This is called ideal Brayton cycle or simple Brayton cycle. Okay. So we came to know that the efficiency is directly proportional to the pressure ratio. So that here we are trying to play with the pressure ratio and we want to see what is the maximum efficiency we can get over here. For that, let's increase the pressure ratio here and see what happens. Let us increase the pressure ratio from, instead of from 1 to 2, let's increase it to 2 dash, right? So when you increase it to 2 dash, so from this point we start supplying the heat until it reaches to the maximum temperature cycle. Why until it reaches the maximum temperature cycle? Maximum temperature of the cycle is always limited by the maximum temperature that can withstand by the materials of the turbine blades. Maximum temperature of the cycle is always limited by the maximum temperature that can withstand by the materials of the turbine blades. So that we cannot cross this point. What is the process you use? This point is limited and the minimum temperature is also limited by the surrounding conditions. Because in the cooler we can use the surrounding conditions. Therefore, we cannot go beyond the minimum temperature also. In that case, from this 2 dash, we can supply at constant pressure. So we can supply heat at constant pressure until it reaches to this point 3 dash. And from 3 dash, it expands isentropically to cooler pressure. This is the 4 dash and 4 dash to 1 is the cycle. Now our new cycle is 1, 2 dash, 3 dash, 4 dash, 1. When you increase the pressure ratio, what we see is this. Now, let us increase the pressure ratio again. This time, let's increase the pressure ratio. Let's increase the pressure ratio to this point, 2 double dash. When you increase the pressure ratio up to 2 double dash, so the cycle will go like this. 2 double dash, 3 double dash, 4 double dash, and 1. This is your new cycle on increase the pressure ratio, right? So let's try to increase the pressure ratio again. So if you go on increasing the pressure ratio, what you see here is your cycle area goes on decreasing. Your cycle area goes on decreasing. But what does it represent? The cycle area represents the net work output of the cycle. If the area of the cycle is 0, it means that the net work output also 0. With 100% thermal efficiency and with 0 work output, what we do with the cycle? Our investment is completely getting vanished, right? So we do not want a cycle with 100% thermal efficiency and 0 net work output. What do you want? We want to see an optimization. We want to see a maximum work at the same time maximum efficiency. Where we get the maximum work and where we get the maximum efficiency, that is important for us, right? So that means here still we have a possibility for optimizing the pressure ratio. We have a possibility for optimizing the pressure ratio. How do you optimize it? To optimize the pressure ratio to get the maximum work, we need to differentiate the net work output to get the maximum work. To get the maximum work, differentiate net work output with respect to pressure ratio and equate it to 0. There you will see that at what pressure ratio we will get the maximum work output. That pressure ratio is known as optimum pressure ratio for maximum work output. On differentiating this, you will see that the optimum pressure ratio is equal to root of T3 by T1 whole power of gamma by gamma minus 1. Or you can write it as T max by T minimum whole power of gamma by gamma minus 1. So either you can write T3 by T1 or T max by T minimum. I hope it is fine. Yes, I am going to deal with boilers and IC engines also. Yes, you can keep in touch, Isaac. So the network output decreases, how the efficiency increases. Yeah, it does not depend on just only network output, right? It depends on network output and heat transfer. So it depends on both the parameters. So if it is showing the network output decreasing and efficiency increasing, means for less heat supplied we are getting more work. That is the meaning. Okay. So this is the optimum pressure ratio for maximum work output. Now we can write here the maximum work equation, that is Cp into m dot into root of T3 minus root T1 whole square. Okay. So this is all about simple Brayton cycle. So as we have limited time, here I am not going to explain about the developments of the cycle. So let's see some of the problems on the simple Brayton cycle and solve them. So first let's try to get the idea on that, and in the next session I will explain the developments of the cycle also. Okay, shall we solve some problems? So as usual, if you have any doubts, you keep on posting your doubts. So here is our first problem. So an ideal Brayton cycle operating between the pressure limits of 1 bar and 6 bar has minimum and maximum temperatures of 300 Kelvin and 1500 Kelvin respectively. The ratio of specific heats of the working fluid is 1.4. The approximate final temperatures in Kelvin at the end of the compression and expansion. At the end of the compression and expansion will be and the expansion process respectively. So one good thing with Brayton cycle is, in almost in all Brayton cycle problems, they just give the minimum temperature and maximum temperature of the cycle and the pressure ratio. They always give the minimum temperature of the cycle, maximum temperature of the cycle and the pressure ratio of the cycle. If you have these three values, so only thing you need to find out is T2 and T1. What else is left? If you have maximum and minimum temperatures, what else is left here? We have T1, you have T3. Only thing is you need to find out T2 and T4. That's it, the problem is over. So if you have all the temperature values, you can play with any value. You can easily find out, easily calculate any value. So let's see here. So finding out T2 and T4 also very easy. So for both, you can get from the isentropic expansion. Please get me the answers quickly. Rashika, practice books means if you want to have textbooks, so one of the books I can suggest you is Senjal, Thermodynamics by Senjal. And for power plant engineering, you can refer the Rajput. Okay. So for any other specific, you can let me know. So could you get me the answers? Yes, 900 is correct. Sorry. Yes, Prashant, you're right. Come on, who are watching on YouTube also, please post the values. That's nice. Simple question, right? In fact, what I am saying is, Brayton cycle problems are always very simple. As I am telling you, they always give you minimum temperature and maximum temperature values, T1 and T3, and pressure ratio. From that, you need to find out T2 and T4. That's it. If you find out those two values, and you can play with other questions also that we are going to see now. But first, you calculate here T2 and T4. It is asked for after the compression and expansion. Here, these are simple mistakes we do here. Even though we get the right answer, sometimes there are possibilities that we go for opting the wrong answer. See here, it is asked for the temperature at the end of the compression and expansion respectively, right? Obviously, most of you got the right answer, that 500, 900 you are getting. But what is 500 and what is 900 is important. Which is after compression, which is after expansion, that is important. Okay? So after the compression, you will see 500 and after the expansion, you will see 900. So this should be the answer, not the B. So both numericals are same. But what is after expansion, what is after compression is important when you see that the process respectively. So some of you are giving B answer. Check with that. I am solving here. It is given that T1 is equal to 300 Kelvin. T2 is equal to, we need to find out. T3 is 1500 Kelvin. And T4 is, we need to find out. RP is the pressure ratio. It is given that P2 by P1 is equal to 6. P1 is 1 bar, P2 is equal to 6 bar. So now, T1 by T2. From the process 1 to 2, what is T1 by T2? RP power of gamma minus 1 by gamma. That is, T1 is equal to, sorry, T2 by T1 is equal to, T2 is equal to T1 into RP power of gamma minus 1 by gamma. So what is T1? 300. What is the pressure ratio? 6.4 by 1.4, which is equal to 500 Kelvin. That is our T2. Now coming to the T4. T3 by T4 is equal to RP power of gamma minus 1 by gamma, where T4 is equal to T3 by RP power of gamma minus 1 by gamma. What is T3? So T4 is equal to 1500 by 6 power of 0.4 by 1.4, where you get 900 Kelvin. That's it. These two are the answers. Very simple. We have to use always these two equations. T2 is equal to this, T4 is equal to this. Always in the Brayton cycle it happens. Fine. Shall we go to the next problem? So A is the correct answer. Now You check with this answer. Same problem. An ideal Brayton cycle operating between the pressure limits of 1 bar and 6 bar has minimum and maximum temperatures of 300 Kelvin and 1500 Kelvin respectively. The ratio of specific heat of the working fluid is 1.4. If the specific heat at constant pressure of the working fluid is 1 kJ per kg Kelvin, the work done by the turbine is dash kJ per kg. Akanksha, how you got 0.4 in this problem? Here gamma minus 1 by gamma. Gamma equal 1.4 is given, right? The ratio of the working fluid is given as 1.4 is given. So from that gamma is equal to 1.4 here. So that 1.4 minus 1 is 0.4. Now get me this answer. It is very easy. The work done by the turbine. What is the work done by the turbine? So now here I am drawing again the TS diagram. So here I also draw the PV diagram. I think someone asked me to draw the PV diagram. I am going to draw the PV diagram also. So this is the turbine work here. We are going to find out. Before that, let me draw the PV diagram. How you draw the PV diagram? This power plant operates between always two constant pressures. So draw the two constant pressure lines first. This is the P2 and you draw another constant pressure line P1. So we start with the minimum temperature and minimum pressure. So this is the minimum pressure and minimum temperature, let us say somewhere else we have here, and take that point and take the compression, isoentropic compression, and PV coordinates isoentropic compression will be like this. So 1 to 2 is an isoentropic compression and 2 to 3 is constant pressure heat addition, 3 to 4 constant isoentropic expansion, 4 to 1 constant pressure heat rejection. That's it. We have 4 components. What are the components here? We have compressor here, we have combustion chamber here, turbine and cooler. 4 components, 4 processes and 4 energy transfers. What are the 4 energy transfer? Heat rejection, heat supplied, work supplied to the compressor. Okay, 4 energy transfers. Now what to find out? You need to find out WT. What is WT? Cp into T3 minus T4. Cp is given as 1. T3 already known 1500. T4 just we have calculated 900. So that what is the answer? 600 kilojoule per kg. Okay. So the correct answer is 600. Come on. Let's go to the next problem. Again the same problem. The cycle operating between the pressure limits of 1 bar and 6 bar, same temperature limits, same working ratio, specific ratio and Cp value. The work supplied to the compressor is, come on, 15 seconds, not more than that. Right, Raunak, Raut, Shubham, that's nice. It's an easy one, right? So, what do you see? WC is equal to Cp into T2 minus T1. Cp is 1, T2 is given, T2 we have found, that is how much? 500 minus 300, which is equal to 200 kilojoule per kg. Over. Very simple. I hope all you got it. Okay, let's go to the next problem. Same problem again. The heat supplied to the cycle is dash kilojoule per kg. For the same problem, what is the heat supplied to the cycle? Quickly, 15 seconds, not more than that. That's right, all you are in the form. All of you are giving the correct answers. Continue. Continue giving more answers so that we can cover more questions. We have only 10 minutes left. Yeah, correct? Correct, Sachin. You have been giving the correct answers. Yeah, Pandey, Yogesh, Jeevan. Prashant, recheck the answer. Gupta, recheck the answer. Anish, correct. Pranav, recheck the answer. Arvind, Subham, Kunan, all you have given the correct answers. Okay, so it is very simple again. What to find out? Heat supplied to the cycle Cp into T3 minus T2, that is 1 into, that is 1500 minus 500. T3 is 1500, T2 is 500. I told you, right? If you have the temperature values, we can play with the problem. We can get anything like this. Okay, once you have T1, T2, T3, T4, that's it. The problem is over. You can get everything. You can get heat transfer values, you can get work transfer values, you can get the net work output, you can get the thermal cycle. Right? See, for the same problem, what is heat rejected by cycle? 10 seconds now. Quickly. Already Syed calculated before I asked the question. Nice. Yeah, Yogesh correct. Akshay correct. Prashant wrong. In such a simple problem, shouldn't give a wrong answer. You cannot find a simpler problem than this problem in GATE exam. Anish correct. Kunan, Shubham, all of you are correct. Sachin is always on the form. What I see is, yeah, good. Sharmila, yeah. Good. Naveen, what is B here? Nothing B here. Okay. Good. All are giving correct answers. That's nice. Okay, I think I don't need to solve this, but let me write Q rejection is equal to Cp into, what is it? T4 minus T1, that is 1 into, what is T4? We have calculated, right? 900 minus 300, that is 600 kilojoule per kg. So now let's go to the next problem. Come on. So the net work output cycle is, come on, take 10 seconds. Net work output. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. Right, Jivan. So net work output is nothing but, here you can check here, what I said, net work output is nothing but WT minus WC or QS minus Q rejection. So you can substitute any two values, you will get here 400 kilojoule per kg. Over the problem. Simple. Okay, here we can say that the first law is satisfied. Right? What does it say, first law of thermodynamics? For a cycle, sum of all the heat transfer is always equal to sum of all the work transfer. Is it true here? So sum of all the work transfers is equal to sum of all the heat transfer and is equal to 400 kJ per kg in the Brayton cycle. That means first law is satisfied. Now let's go to the next question. So thermal efficiency of the cycle. Get me thermal efficiency of the cycle for the same problem. Hi Gopi Krishna, study plan I will explain in the next session as we don't have much time today. Let's solve some more problems. Definitely I will elaborate the things in the next session. Why Kunal 40.06? Okay, I hope we have used RP. Fine. So you can find out thermal efficiency in two ways. Either you can take simply net work output by heat supplied and is equal to 400 by 1000. So this is equal to 40%. Or you can use thermal efficiency of the Brayton cycle 1 minus 1 by Rp power of gamma minus 1 by gamma, which is approximately equal to 40%. Right? Yeah, I want you to solve this problem. This is one of the important problems. The same problem again, but here one extra thing we see here is isoentropic efficiency of the turbine is given. Isoentropic efficiency of the turbine is 90%. You need to find out net work output cycle. So how do you solve when you come across isentropic efficiency? What is isentropic efficiency of the turbine? Isentropic efficiency of the turbine is nothing but actual work, the turbine actual work to the turbine isentropic work, right? Therefore, the turbine actual work is equal to efficiency of the turbine into efficiency of the turbine into isentropic work. Isentropic work means what we have calculated, and turbine work is 0.9, turbine efficiency is 0.9 and turbine work is 600, right? So which is equal to 540 kilojoule per kg. This is what we see. So when it is given that isentropic efficiency, that means we need to consider irreversibility also. If it is given that isentropic efficiency of the turbine, it means that we need to consider the irreversibilities or losses in the turbine also. And consider the losses, we lose some work. Actual work is in ideal case work we should get is 600, but on consider the losses 10% we need to spend to overcome those losses, frictional losses, heat losses, whatever. So to overcome those losses 60 kilojoule we have spent, so that we are left with 540, right? So now let's go to the Rajshekar, stay in touch with Gradeup, so we can get contacts of us. So find out thermal efficiency. Just I would like to for the same problem again. So we have here isentropic efficiency of the turbine 90%, and we need to find out the thermal efficiency of the cycle. Okay. So when it is given that isentropic efficiency, just I would like to show you the how to draw the Brayton cycle also. There will be small change in the Brayton cycle. For an ideal Brayton cycle, 1 to 2, 3 to 4, 4 to 1. 3, 4, 4 to 1, right? This is the ideal Brayton cycle. So when you consider irreversibilities, this 3 to 4 takes a new path. It deviates from the isentropy path and takes a new path, and it goes like this, 3 to 4 dash. And overcoming the frictional loss and all, this 4 will become 4 dash now. This efficiency of the turbine we can write like this also. T3 minus T4 dash, Cp into T3 minus T4 dash is the actual work, Cp into T3 minus T4 is the ideal work. From this we can calculate T4 dash also if it is required. For this problem it is not required, but in coming problems it is also required. Okay. So for that, what is asked for? You need to find out thermal efficiency of the cycle is nothing but net work output by heat supplied. What is the net work output? Turbine work minus compressor work by heat supplied. What is the turbine work? 540 now, minus compressor work remains same, 200 by heat supplied. So it is equal to 34%. I hope all of you got the right answers. Yes, Nagarajan, I am going to cover the full thermodynamics syllabus. Stay connected with Gradeup. Now let us look at this problem. In this problem, again it is the same problem. What we see here is the isentropic efficiency of the turbine as well as the isentropic efficiency of the compressor. It is 90% for turbine, 80% for the compressor. Please consider this 80% also. Now get me the net work output of the cycle. What is the answer? What do you see? If you consider the compressor work, what is the isentropic efficiency of the compressor? For the compressor, it is compressor work, isentropic work by actual compressor work. In case of compressor, actual work is more than isentropic work, so that it will come in the denominator and isentropic work comes in the numerator. In case of turbine, isentropic work will come in the numerator, actual work will come in the denominator. Sorry, for this actual work will come in the denominator, for turbine it will come in the numerator. Okay, so here we can calculate the actual work of the compressor, that is 200 by, it is given that the compressor efficiency is 80, therefore it is 250 kilojoule per kg. Now the net work out to the cycle is equal to WT actual minus WC actual, that is 540 minus 250, which is equal to, what is the it is 290, it is 290. Yeah, okay. Because that's how actually I would like to cover a few more problems also, but as we have not sufficient time, this you can see here, you need to find out the optimum pressure ratio by taking root of T3 by T1 whole power of gamma by 2 into gamma minus 1, and this you can find out by using Cp into root T max minus root T minimum whole square. And also after the class you can solve this problem and you can post in the YouTube box, that is thermal efficiency of the cycle. When you have the turbine efficiency is 90% and compressor efficiency is 80%, and thermal efficiency of the cycle is, you take only net work output by heat supplied. Calculate net work output by heat supplied. Don't use 1 minus 1 by Rp power of gamma minus 1 by gamma. 1 minus 1 by Rp power of gamma minus 1 by gamma can be used only for ideal Brayton cycle, not for actual cycles. Okay, now if you have any irreversibilities in the cycle, if you consider the isentropic efficiency of the turbine and compressor, we should not use the ideal Brayton cycle efficiency equation. This is applicable for either reversible or irreversible processes. Irrespective of that, you can use this. Better use always this equation. And your heat addition also changes here. Just I am drawing a diagram here for you. This is your ideal Brayton cycle, right? 1, 2, 3, 4. If you consider the irreversibilities in the cycle, this 1 to 2 takes in new path 1 to 2 dash, and 3 to 4 takes in new path 3 to 4 dash. Already we have calculated WT during this process, WC during this process. Now what is your heat supplied here? Heat supplied is equal to Cp into T3 minus T2 dash, not T2 here. That means we need to calculate the heat supplied again. So for that you can use efficiency of the compressor, that is Cp into T2 minus T1 by Cp into T2 dash minus T1. From this you will get the T2 dash, substitute here, you will get the heat addition. From that you can calculate the thermal efficiency cycle by using net work output by heat supply. Same if you have to find out heat rejection, we can use Cp into T4 dash minus T1, not T4 minus T1, because the gas entering the cooler with T4 dash. Here the gas entering the combustion chamber with 2 dash. Okay, now you have to calculate the heat supplied from this point, not from this point. So T3 minus T2 dash is the heat supplied, T4 dash minus T1 is the heat rejection. I hope you like the session. Okay, so we will continue the live sessions for more and more topics. So see you.